think we're ready. I'll be the normal thing. You'll present, I think, for 45, 50 minutes.
Yep.
And we'll do questions with the public, this is a big room, so that could take a while, I guess. And then we'll obviously do the closed door session. I think you're recording, right?
Yes, I'm
Which is
recording.
totally fine. Once we get to the closed door session, just remember we should stop that
Yep.
part. Okay, I guess just maybe a few comments. I'm your advisor. You are the first student I had at Michigan. You started, I think, summer of 2020 in the middle of the pandemic. So I don't know how many people started at that time, but that was not the best time to start. And oh yeah, so this is Shih-Chi and I in my backyard with my sons. He was, I guess, 3 or 4 at the time.
Yeah.
So he had like the sidewalk chalk. And so we couldn't come to campus, so we were out in our backyard. Sometimes we were in our front yard, and neighbors would come by the next day and see all these equations on our driveway. And be like, what is this kid's? Is he doing to his son? My son's a super genius. He's doing PhD work already. No, it was GPS hiking out in the front yard doing stuff, and it's been a great ride. I know there's been some ups and downs through it, but you're here, and I'm excited for your defense. And without further ado, I'll let you kind of take the time. The floor is yours.
Thank you, Peter. Thank you. This is my honor to work with you over the years. I'm very excited today to share with you about my dissertation titled with Stability Analysis of Quadratic Dynamical System from Convergence to Boundedness. This is a picture of physical experience that we do on a fluid dynamics system that we put an airfoil in a string of air. And you can see a lot of activities happening downstream of the airfoil. This behavior is very important for us to fly an aircraft safely. And not just aircraft, this kind of flow analysis actually shows up in many kind of different engineering domains, including renewable energy for wind farm control, and also for data center that running ChatGPT or anything like that. However, this kind of experience is still challenging because the complex nonlinear dynamic in the system. We need a very intense and careful setup to have the experiment ready and easy to use. What if we have a tools that can help us accelerate this whole process and give us some guarantee on how the system will perform if we actually run it in real life? And after like 5 to 6 years, I make some contribution over to this problem. In here, we developed some extensible stability analysis method that can provide some behavior guarantee that is useful for safety and reliable operation and design in the engineering system that involves fluid dynamics. Today, in this following 14 to 15 minutes, I'm going to share a few what we discovered on the journey and hopefully have some interesting story to share. In engineering project, we typically start with this nonlinear complex system. And we start with a set of requirements that we want this system to satisfy or to do or not to do. With this set of requirements, we'll go through a series of modeling, design, and analysis that capture the essence of what we care about and do design around it and analysis to make sure we can actually achieve it. This is an iterative process that you might do some analysis and figure out you need a better model to capture the essence of the dynamics. And after the whole process, you will get a certificate that help you to check whether you satisfy a certain behavior or not. And as you can see, the modeling side showed up in the very beginning of the engineering process. Therefore, the choice of a model is very important in the whole engineering cycle. If you choose a linear model, it's fairly easy to work, but in terms of modeling the behavior of the system, it can be very accurate because most of the real-life system is nonlinear. On the other hand, you can choose a nonlinear system. It can provide a very accurate description. However, working with them, doing design and analysis on that is still challenging. Therefore, a descriptive but tenable models is very essential for good control performance, especially for the complex dynamic we are trying to look at. Quadratic dynamic model in this form is a nonlinear ODE not motivated by Navier-Stokes equation. It is structurally simple. You can see that it only involves 3 terms: constant term, linear term, and a quadratic term here. But it can capture a wide variety of behavior. That includes limit cycle, bifurcation, and chaos. And those behavior are very important for nonlinear system, and that could not be captured by linear model. And among all this different behavior, there's one most important property we cares about. It's called stability in control system. That is the foundation for everything we can do as an engineering for dynamical system. In plain word, stability means the ability to stay consistent behavior. For example, if you are flying an airplane, you might hit some turbulence on the way here, and the airplane will start jiggling up and down, and eventually it will come back if we design it correctly. And at the same time, it does not go very far away from the desired trajectory. Otherwise, it might hit the other airplane. There are 2 things happening here. The first thing is called convergence. That means the system will go to a desired state that we design. And the other thing is called boundedness. That means the system does not go far away or go into some undesired state. These two properties of the stability are fairly easy to understand in a linear setting. However, in a nonlinear setting, it is hard to do that, and we need a guarantee for these 2 properties specifically for any useful engineering project. Therefore, to effectively utilize the quadratic models, we need a nonlinear stability with guarantee. In this dissertation, we start with the complex nonlinear system and want to give some certificate on the right here. And we utilize a set of tools from control theory that has a long-standing history all the way back to 1960s. That involves this 4 steps. Don't worry about it at the moment. I'll explain it later. In the first part of my dissertation, I've utilized this framework to focus on this property called convergence. And I make 2 specific contributions for the particular quadratic system we are looking at. In the first contribution, I provide a tighter characteristic that understand the nonlinearity better. And the second contribution is how we look at the optimization problem involved in this analysis and provide a more efficient algorithm to solve it. In the second part of my dissertation, I extend the framework into the boundedness analysis. That we also make 2 contributions. The first contribution is that we propose a convex approach to solve the condition. And the last contribution in my dissertation, I look at what is a theoretical limit if we are using this whole pipeline to do the boundedness analysis. And here's a list of publications over the years. Beside the dissertation contribution that I mentioned, we also extended to a modeling process of the engineering project and also has some refinement in the whole framework. Besides that, I also work a little bit in safety critical control if there are some uncertainty in the system. With that, hopefully I gave you a very, very, very high level of what my dissertation is working on. Now, I would like to walk you through the whole framework using the example of convergence. Here is a formal definition of what the problem we are looking at. So we are considering a system x dot equals to ax plus phi of x. Now I'm neglecting the constant term because we're looking at the local stability of the origin. And the specific stability property we are going to check is that is this yellow circle a region of attraction, which is a region that whenever you start in that region, you will converge to the equilibrium point. So we got a system and we got the question we want to answer. One thing one very naive idea you can do is you sample a bunch of a point inside a circle and run a simulation to check whether they converge to the equilibrium point or not. However, this process is challenging, especially when you go to high dimensional, you cannot sample every possible point in this region. Therefore, we come to the framework that can provide us a guarantee. The first step of the framework is called separating the nonlinearity. Now we start with the original closed-loop system, and we go through a linear factorial transformation that separate the system into two parts. The first part is the linear part at the bottom, and the second part is the nonlinear part at the top. By doing this, we're basically separating the easy to understand part, and the hard to handle part. On the bottom here, we have a lot of tools to do it. If we can capture the upper part, the nonlinearity part, in some way, we can utilize the linear analysis down here to provide some guarantee on the whole closed-loop system. So that comes to the next step that we want to characterize the nonlinearity in the top. And you can observe that the linear part of the system only affect by the nonlinearity through its input and output x and z. So if we can find a tractable input-output characteristic of this nonlinear system, then we can use it in the analysis. And the characteristic we're going to use here is called quadratic constraint. It is a quadratic relationship between the input and output of the nonlinearity that is characterized by this matrix N. For example, if your nonlinearity is phi of x equal to x squared, and you define the output as z, you can actually find this quadratic constraint that inside this -1 and 1 region. Visually, this blue curve is the square of the input, and this green curve is the square of the output. And in this -1 to 1 region, you can see that every part of the blue curve is above the green curve. And we can show that analytically this inequality holds in this region. And you can do this similar to other type of nonlinearity or other region as well, but it requires different form of the matrix N here. So with that, we are ready to propose the stability condition. And the main tool we are going to use here is called certificate function. It is a function v of x that has a value, is a value function that has two main properties. The first property is that it is positive in the domain, and the time derivative of it along the system trajectory will be negative. And these two properties can help us guarantee the stability property of the system. In the literature, it takes a form of the Lyapunov function or storage function for a dissipated system, or barrier function if you cares about the safety of the system. Visually, people typically have this bowl shape of function and say that on each point of the bowl, the dynamic carry it to the bottom of the bowl. Therefore, you can translate that to the stability of the bottom of the bowl, which is the origin, is stable. Now let's look back to our problem. We got a closed-loop system, and we got a quadratic constraint to characterize the nonlinearity. And we can consider a quadratic candidate function that in this x transpose p of x form, and the p is a positive definite matrix. That means every eigenvalue of p is a positive value, and the v of x can guarantee to be a positive value for any non-zero x. To verify the second condition that decrease along the trajectory, we can utilize this matrix inequality. And if we can find a multiplier c here, such that this matrix inequality hold, then we can guarantee that the time derivative of v is less than 0. You can show this by multiplying the input and output on the left and right side. And this part is the quadratic constraint we characterized in the previous step. And this part is always positive. So the sum of the the time derivative of the output function and a positive term is negative, you can guarantee this part is always negative. With that, we can actually find the characteristic of a region of traction in the system. So now we have the condition that guarantee the stability of the system. But the question is that how do we actually find this P and C here? So that comes to the last step of the framework. Basically, we want to find these two, one matrix and one scalar, such that this inequality hold. And this type of question actually falls into a class called semi-definite program. That is an optimization problem involve matrix inequality in the constraint. And we can solve it using convex optimization. And there are a few benefits of it. The first one, because we're using an optimization formulation, we have a very flexible problem formulation that we can minimize or maximize some quantity subject to the constraint. And the second benefit is that we have a strong theoretical understanding of this type of problem. We can know when it can be solved, and we can also show that if it cannot be solved, we can provide a certificate that the condition cannot be solved. And lastly, we have a lot of reliable numerical library existing that we can solve it we can implement the problem very easy and solve it quickly. So at the bottom of this pipeline, if we get a feasible solution from the convex optimization solver, we basically get a certificate on the stability guarantee for our system. So this is a pipeline. Here I'm going to talk about what a specific contribution we made for the quadratic system. If you closely look at the nonlinearity in the system we care about, there are two major types of nonlinearity. The first type is called sign-definite. That basically means the nonlinearity is either always positive or always negative. But for a sign-indefinite nonlinearity, the value of the nonlinearity can be either positive or negative given different input. And this blue curve, this green surface is the exact nonlinearity we care about. And this blue curve is what people propose in the literature that use the quadratic constraint to bound it. And on the left here, you can see this taco shape is captured pretty well by the blue surface. But on the right here, you can see there's a couple gap around the nonlinearity. Therefore, this specific observation leads to our contribution. The process we're taking here is that we sample a bunch of points on the exact nonlinearity, this green surface, and we set out an optimization to minimize this specific gap. And with that empirical quadratic constraint, we prove an analytical one that can guarantee us we have a quadratic constraint that specifically bound this direction. And that's what we propose called value quadratic constraint. And you can see that this red surface lies on top of the green exactly along this direction. And you can also prove it like mathematically here. So with that, there are a few implications. The first one is that because the whole quadratic constraint framework, we can characterize the same nonlinearity using multiple quadratic constraints. We can actually jointly characterize this green surface fairly well by using the one from the literature and the one we propose in this dissertation. And not only just for this simple nonlinearity, we can extend this idea to other type of nonlinearity that the Hessian is sign indefinite, or you are capturing the cross coupling between two nonlinearities. So with this better characteristic of the nonlinearity, we can test it out how it plays out in the framework. So this is a numerical example that has two states. The graphic here shows all the trajectory converge to the origin here, beside the red region on the top right. And those are the region that the trajectory does not converge to the origin. So we can see that the largest spherical region of attraction in this equilibrium point here is around 4.9. And by using our framework to do the analysis, the first set in the blue is what people do in the literature, that the quadratic constraint that does not capture the specific landscape of the nonlinearity we cares about. And the proposed quadratic constraint that includes the valley can perform better and give you a better region of estimation for this specific system. So basically, in this chapter, we propose a new quadratic constraint that capture the specific nonlinearity dynamics here and reduce the conservatism in the analysis framework. So that's the first contribution I made. And the second contribution is about how do we actually solve this optimization problem. So if you look at the problem again, we are actually setting out an optimization problem that involves 3 sets of variables. The first set of variable alpha and E is what we cares about in the local region. And the second set of variable is this green area. That's the Liaopeng function we cares about. And last one is the matrix we cares about, the size of the region of attraction. And this constraint here is actually a non-convex constraint because it has a complex interplay between the local region and the Liaopeng function you choose. And in the literature, people solve this by grading over the shape, the size, fixing the shape of the local region and grading over the size of the local region. And for each point on the grid, you can solve a SDP to get a point like this. So if you solve this problem, you might think the maximum could be here. And for this 2 specific grid, the SDP is actually infeasible. In this chapter, we look at this problem specifically and try to understand how does this R related to the size of the local region we cares about. And we sample a bunch of different systems, and most of them comes out with this type of shape. And we look further into it and figure out that this alpha actually has a limit that beyond this limit, no problem will be feasible. So we can show it by mathematically prove it. And with this knowledge, we can actually develop more efficient algorithm that using bisession search to identify this critical point here. And also, we observe that the function here is mostly unimodal, so we can use a golden session search to identify the critical point here. We utilize this set of algorithm and successfully speed out a whole number of we reduce the number of SDP you need to solve by about like 75%. Even though we did not manage to prove that the function is a concave function, but we did show that in the 1D case, this is actually an exact point. But for a high dimensional case, we cannot really show it. So up to now, I covered the convergence and the first 2 contribution in the dissertation. And the next part, I will talk about the boundedness, how we extend the whole analysis framework to this another set of stability property. So here is a system called Lorentz attractor. This is a system that exists a chaotic behavior. That means for any small amount of difference in initial condition, the 2 trajectory will eventually become very different from the simulation. And in fact, this system has 3 equilibrium points, but none of them are a stable equilibrium point. Therefore, the region of attraction analysis we are talking about does not apply anymore. However, you can see that all the trajectory kind of fall into this butterfly shape. In fact, if you simulate any trajectory that is far away from the origin, it will come to this butterfly shape and stay on it. So this is what people call boundedness. This is reflecting the nature behavior of many physical fluid that you cannot go to infinity by nature. And this property is important for long horizon simulation, especially for weather simulation or other type of fluid application. So here comes the problem that we have this complex nonlinear system, and we want to check this problem. How do we know when the given model is bounded or not? So let's look at what we are looking at. So this model we are looking at here is x dot plus c plus lx plus phi of x. Now we are including the constant term because we are modeling a fluid dynamic system. We don't essentially assume we shift to an equilibrium point. One important assumption here is that this nonlinearity is lossless. That means the inner product between the input and output of it is 0 for all the x. And this is an assumption based on the Navier-Stokes equation that the nonlinearity does not generate or dissipate energy in the dynamics. And you can see that this is actually in the quadratic form. We can write it in this way. So that gives us an opportunity to put the whole analysis into our framework. One technical note here is that this specific property is preserved under the change of a coordinate. If you define a new coordinate y that shift the original coordinate by n, you will get a new set of ODE. However, the nonlinearity will remain the same form. Therefore, the lossless condition will stay the same. And in the literature, Schlegel and Noah in 2015, they proposed looking at this problem by a notion called trapping region. Basically, they use a kinetic energy, that is a certificate function we were talking about, that takes the form of 0.5 of y transpose y. That is the kinetic energy at a new coordinate. And if you take the time derivative of it with respect to the system dynamics, you can see that this lossless property shows up, and that means the nonlinearity does not exchange any kinetic energy in the system. Therefore, the kinetic energy only be affected by the constant dynamic and the linear dynamic here. And you can see that this term is quadratic in y. So if you have a large y, that term will dominate the first term. And Schlegel Noah proposed that if this matrix is a negative definite matrix, that means for any y, this quantity will be less than 0. If you have a large enough y, you can guarantee that this k dot is less than 0. That means if you are far away from the phase plane, you will eventually come closer to the origin. But if you have a smaller y that is closer to the origin, we cannot guarantee anything happen between the constant dynamic and the linear dynamics. And with this trapping region, we can show that the system is actually bounded because if you are far away, you will get pulled into the origin, so you are not diverging to the infinity. However, in the literature, they don't have a reliable numerical approach to verify this condition. And to put that into our framework, we have this lossless quadratic constraint that is the assumption on the system. And we have this trapping region as the stability condition we care about. Now I'm going to introduce how we solve it using convex optimization. So if you look at the condition closer again, this AS matrix is actually a linear function of n, which is the coordinate shift we are trying to find. And the LS and the Q are the system matrix that are given by the model. And because of this linear dependency on n, we can set out a semi-definite program that solve this, minimize the A, that is the upper bound of the eigenvalue of AS. If you solve this problem and get an A star that's less than 0, we basically get a guarantee that there exists an N star such that this AS is negative definite. And by the theorem, we can verify that a trapping region exists and the system is bounded. And if A star is positive or non-negative, we can also guarantee that no such a coordinate shift can render this matrix being a negative definite one. And therefore, no trapping region will exist in the system. So with this semi-definite program, we basically get a reliable numerical approach to certify the existence of trapping region. And moreover, we can actually characterize the size of it. In the literature, they use this K dot to estimate the size of the trapping region. However, their estimation is actually a worst case estimation, and often it is overly conservative. Turns out we can actually solve this size exactly by setting out this optimization problem. Basically, we are finding the furthest point in the set that energy can grow. That means for every further point, the energy is always decreasing. And then the optimization problem in this form is actually a non-convex problem that we call quadratic constraint, quadratic program, with this matrix being a negative definite one. So this constraint is actually a non-convex constraint. Nonetheless, we can formulate a dual SDP by a process called S procedure. That is a convex problem, and we can show that it does not have any duality gap, meaning that if we solve this dual SDP, we get the exact solution of this primal problem. And lastly, we can actually recover the primal solution of Y from the optimality condition called KKT conditions. And here's a numerical example that we show the Lorentz system. It is a 3-state system here. And you can see all the trajectory in the gray will converge to this butterfly shape as we talked previously. And the process we do here is to first use the SDP to verify there exists a trapping region by finding this coordinate shift, this triangle here, that we know every trajectory will eventually come close to it. And then we can solve the second SDP to find the exact size of this trapping region that I write in the red circle. And the blue circle is what people do in the literature. You can see that they have a much larger estimation of the trapping region. And our analysis get a much closer to this butterfly shape. And lastly, you can recover the critical point that shown in this purple diamond. That is where the system has a qualitative change in terms of this kinetic energy. And you can see that all the trajectory eventually comes down to this point, and I'm showing the energy plot of the sample trajectory. Now we can guarantee the system will stay below this energy. So with this convex process, we can actually extend it to other phase of engineering process. Here we are providing an example in modeling phase. Because our constraint is a convex constraint, so you can put it into any optimization problem and find a very easy way to solve it. Here we are using a data-driven modeling algorithm called Cindy that developed by Stephen Brownton and Nathan Cruz. And with this original Cindy algorithm, it only tries to balance between the accuracy of the model and the sparsity of the model, which is how simple your model can look like. And now we are adding another constraint is what we analyze the boundedness, because the original algorithm does not produce any guarantee on the system whether they will be bounded or not. With this additional constraint, we can actually construct a model that can guarantee the bounded property of the system. Here I'm showing airfoil simulation that we have a numerical computational fluid dynamics solver that get to project by some projection step. And then we use that as the initial condition of our model and run the simulation for about 5 seconds. And you can see that our model gives us a very accurate approximation to the exact numerical simulation from the top. That is project down to the low order space. And these two figures are very close to each other. And now we can use our model to replace the very costly simulation on the top for the purpose of our analysis. If you want to do other type of analysis, you still need to run the simulation, but we can run much smaller amount of simulation now. So with this convex optimization problem that we bring the whole boundedness analysis into our framework. And the last part of my dissertation, I look at how conservative is this process. So up to this point, we are actually using the sufficiency to prove this specific property. For convergence, we use region of attraction as a characteristic of the convergence and propose that those matrix inequality as a certificate of a region of attraction exists. And similarly, for the boundedness, we use trapping region as a characteristic and use that matrix inequality as a certificate of trapping region exists. So you can see all the arrow is pointing to the left. There are some work that try to provide arrow to the right. However, this reverse direction is much more challenging because you want to verify all the system behavior by altering the trajectory and provide an algebraic condition to show that property. However, in the literature, also in Shih-Chi and Noya in 2015, they have a theorem pointing to that direction with some technical assumption, saying that if the system is bounded with that technical condition, you can show this matrix is negative semi-definite. And this is very surprising to us because they are using a single Lyapunov function to show this sufficient and necessary conditions. So we are really curious about it. And to understand it deeper, we use a very low dimensional scenario to understand how this theorem plays out in that setting. Where we fall back to the wisdom that you try to find the simplest problem you cannot solve and try to understand it and get more insight, and hopefully it can translate to a scalable way. So we first look at a two-dimensional system with some math and coordinate transformation. We actually comes down to this condition here that we want to find a set N1 and N2 such that this matrix inequality is negative semi-definite. And if you are an LMI wizard, you can figure out that only this L22, the sign of this L22 matters in this problem. So we look at it and see that the only case that this matrix has a positive eigenvalue is the case that L22 is positive. And if L22 is positive, we can actually further show it this system is unbounded. And by contrapositive, we show the condition actually holds with our independent proof. So the 2D case is good for this theorem. And how about 3D? So what we do is sample a bunch of systems and try to look at their property. And what we arrive is that a system that is the origin of it is globally asymptotically stable. That gives us a proof it is a bounded system. And also it satisfies the technical condition stated in the paper. However, if we run the LMI, we can get a certificate that any coordinate transformation can render this matrix to be a negative semi-definite matrix. So that gives us a counterexample in 3D that shows that this theorem is actually an incomplete theorem. And there are some implication here by we don't have a necessary direction. So the first implication is that the traffic region condition we have on the top is actually a conservative sufficient condition for boundedness. And this shows up in the over approximation of our estimate region. As you can see, the butterfly shape actually locate on the bottom of the circle we estimate. So if our theorem is conservative, then we are not necessarily capturing the exact bounded region. And the second implication is that the theorem we have in the top actually does not apply to other strange attractor that is known to be bounded, and people have studied in the chaotic community. To address this issue, we have an ongoing work that try to reduce this conservatism, that we are relaxing the lossless quadratic constraint we have in here. It used to be an identity matrix here, but we are relaxing it to a general matrix that helps us capture a wider class of the system. So with that, I covered my dissertation that we start from a complex nonlinear dynamics that we want to give a stability guarantee that focus on two specific stability property in convergence and boundedness, and we make 4 specific contributions throughout the years. And with this development, we provide us extensible framework that can help us better utilize the quadratic dynamics in the engineering project. With some thought of future work, besides looking at quadratic nonlinearity here, we might also look at other type of problem that is actually have higher order nonlinearity. People in the literature has shown that you can actually turn other type of nonlinear system into quadratic system. So if you can bring that in, we can use the same framework to do the analysis. So that is the first future direction. And the second future direction is as I mentioned earlier, we can extend a framework into the modeling process and also the design process. Or if you're curious about safety, that could also be applied. And one last future direction I want to mention is that we can actually close this loop of the framework. So by solving the optimization, because we are using convex optimization, we not only get the primal solution, we also get the dual solution, which is often characterizing the qualitative change in the system. And by those dual solution, we might be able to find some critical scenario that we cares about in terms of either stability or safety. And with those situation, we can run a simulation and have an automatic characteristic process that in the quadratic constraint framework that specifically characterize the nonlinearity over that region. And if we can capture that region better, we might be able to get a better analysis on that specific property. So with that, I have covered